take a second right now, like wherever you are, and just look down at the clothes you're wearing.
Always a good place to start.
Right. Just look at the weave of the fabric or, the stitching on the seams, maybe the embroidery on a logo.
Yeah.
Because we interact with textiles literally every single day of our lives. But, well, we rarely stop to think about the massive, thunderous machines that are required to actually weave, knit, and embroider those fabrics.
Oh, absolutely. The scale of it it's hard to wrap your head around if you haven't seen it.
Exactly. And what is truly fascinating is that right now, those behemoth machines are undergoing this, massive, silent revolution.
Yeah, it's a complete structural rethink. I mean, we're talking about moving away from centuries of industrial tradition,
Right.
which has heavily relied on cast iron and steel, and they're completely rewiring how manufacturing works, really at a foundational level.
Right. And it turns out the solution driving this whole revolution is hiding in the way we use aluminum. So we're looking at some research today from Eleanor Industries. They're a premier aluminum extrusion supplier based in Gujarat, India, and they break down exactly why this shift is happening.
It's a great piece.
It really is. Their article, What Should You Know Before Investing in Aluminum Textile Machines? It lays out the mechanics of this whole transition.
Yeah.
And our mission today for this deep dive is to explore why swapping out traditional steel for, precision-engineered aluminum is totally upending the textile industry. And, of course, to extract the brilliant lessons this holds for modular design and long-term return on investment.
Because when you really dig into it, it's about how a single change in your foundational material, how it ripples outward.
It changes everything.
It really does. It affects speed, it affects energy consumption, maintenance, and ultimately a factory's ability to adapt to an unpredictable future.
It's so exciting that a totally niche B2B manufacturing topic actually gives us this brilliant masterclass in systems thinking.
It's a perfect case study.
Right. So welcome to the conversation. I promise you're going to have some real aha moments today about this hidden world of manufacturing.
Definitely.
But to really appreciate the impact of this shift, we kind of have to start by understanding the battlefield.
Yeah, the factory floor itself.
Exactly. Before we get to the aluminum, we need to ask, why is traditional machinery suddenly failing to keep up? Because for generations, steel has basically been the undisputed king of the factory floor.
Well, yeah, steel is it's what we naturally picture when we think of heavy industry.
Big, sparks flying, heavy metal.
Exactly. It's heavy, it's highly durable, it can take a beating. But the status quo is shifting because, well, a textile factory is an incredibly hostile environment.
Right.
It is not just, a quiet room with some spinning spool.
No, I mean, you think of textiles and you think of soft fabrics, but the reality of producing them is brutal.
Intensely brutal. A modern textile plant operates at very high humidity levels.
So why the high humidity?
Oh, to keep the yarns from snapping during high-speed production. Oh.
So it's humid, and then you have constant chemical exposure from sizing agents, dyes, various wash treatments. And then there's the most insidious factor.
Which is?
The lint.
Lint. Really? I mean, I clean the lint trap in my dryer, but it doesn't exactly seem like an industrial menace.
I know, it sounds minor, but in a factory setting, microscopic fibers are constantly airborne. They settle on absolutely every single surface.
Oh, wow.
But here's the kicker. Lint is highly hygroscopic.
Meaning it pulls water from the air.
Exactly. It absorbs ambient moisture from that highly humid factory air. So what you end up with is this damp, chemically active blanket of fibers basically coating the machinery.
Okay, let's unpack this. Because if you have a machine built entirely out of steel,
Right.
and it's sitting in a highly humid room covered in what is essentially a damp chemical sponge, I mean, that's just a recipe for disaster. It's like driving a classic steel car on salted winter roads every single day. Eventually, the corrosion is just going to catch up with you. Precisely. The rust is inevitable. And in a machine operating at high speeds, with incredibly tight tolerances, rust isn't just an aesthetic issue where the paint flakes off.
It's structural.
It is a catastrophic operational failure. Rust degrades the moving parts. It creates friction where there should be perfectly smooth motion.
Ruining the alignment.
Right. It ruins the micro-alignment of the gears, and eventually it forces the whole factory to shut down for costly maintenance.
So, okay, that naturally explains the push away from steel and toward a metal like aluminum, which, naturally resists that kind of oxidation.
Yes.
But I have to push back here because physics is physics.
Sure.
If you're running a high-speed loom, That machine is violently throwing mechanical arms and shuttles back and forth, right? Sometimes thousands of times a minute.
Yes, the kinetic energy is massive.
Right, so you need mass to absorb that kinetic energy, don't you? Like if you swap heavy, dense steel for a much lighter metal, doesn't that risk the machine just, well, shaking itself apart under those intense vibrations?
It seems totally counterintuitive, right?
It really does, to take weight out of something that violently vibrates.
What's fascinating here is that this is exactly the instinct most traditional mechanical engineers have when they first look at this.
They just assume weight equals stability.
Exactly. But the aluminum we are talking about here is absolutely nothing like the thin metal of a soda can. We aren't talking about flat sheets of light metal just, bolted together. We are talking about highly engineered machine sections. And this is where the manufacturing process called extrusion changes everything.
Oh, okay. Let's break down extrusion then, because that's kind of the core of how this whole structural rethink works.
Right. Imagine pushing Play-Doh through one of those shaped plastic molds, a star or a square.
Yeah, like when we were kids.
Exactly. Extrusion is exactly that, but the Play-Doh is semi-solid aluminum heated to around 900 degrees Fahrenheit.
Wow, okay.
And it's being forced through a hardened steel die under literally thousands of tons of hydraulic pressure.
So you can create these really continuous lengths of very complex shapes.
Exactly. By extruding the aluminum into very specific, mathematically calculated geometric shapes, engineers achieve this incredible structural rigidity without the sheer mass of steel.
That's wild.
It is a complete paradigm shift. You stop relying on brute force weight, and you start relying on structural geometry. A hollow aluminum tube with internal cross-bracing can resist torsion and bending incredibly well while weighing just a tiny fraction of a solid steel beam.
That makes perfect sense. So it's not about the bulk of the material, it's about how cleverly you arrange the structure.
Exactly.
And that idea of precision over mass leads us directly into exactly how these new machines are built. It's not just the metal, it's the specific profiles they are extruding.
Right. The source material details several specific profiles that make this modularity possible. For instance, you have hollow boxes, which provide an excellent strength-to-weight ratio for the main structural frames of the machines. Then you have structural channels.
And those channels are left open, right?
Yes. They offer open, protected tracks built right into the frame itself.
What are they used for?
Running electrical cables, pneumatic lines, and drive belts safely away from the moving parts.
Oh, that's smart.
And then there are custom die extrusions, which are tailored for very specific, unique machine fits, say, the exact curvature needed for a specific embroidery head.
And these profiles are going into everything. The Eleanor article mentions high-speed looms, complex multi-head embroidery machines, knitting machines, and even the massive air handling units and conveyor supports that, move materials around the factory floor.
They're ubiquitous.
But there's one specific profile mentioned that I find absolutely brilliant. The real star of the show here, the T-slot.
Oh, yes. The T-slot has completely revolutionized industrial assembly.
Yeah.
It's an extruded aluminum profile that features a continuous T-shaped groove running down its entire length on one or more sides.
It's industrial Legos. I mean, that is the only accurate way to describe it.
It really is. Instead of drilling a hole and tapping threads every single time you want to attach a component, you just drop a specialized T-nut into that continuous groove.
You drop it in, you slide it exactly where you need it, and you just bolt your next piece directly to it.
Yep.
It's wild to think about a factory manager being able to reconfigure or expand a massive machine without needing a blowtorch or complex welding.
Well, this is the very definition of future-proofing a production line.
Yeah.
Think about a traditional steel setup. Once a massive knitting machine is welded and bolted together, it is entirely static.
Right, it's permanent.
If consumer trends change or your business grows and you need to, say, add a new automated tensioning module to your line, you are looking at heavy fabrication.
You'd have to shut down the entire section of the factory.
At a minimum.
Bring in specialized welders, deal with the fire hazards of sparks flying around highly flammable textile lint, physically cut into the steel frame.
Which means days or weeks of downtime where you aren't making products, you're losing money. But with these standardized aluminum T-slot profiles, you are no longer locked into that static layout. You can scale production dynamically.
That's huge.
You unbolt a section, slide the new module into place along the T-slot, tighten the bolts with a wrench, and you are back up and running.
So your equipment can evolve exactly as rapidly as your business demands grow.
Precisely.
So we have these rust-proof, highly modular Lego-like frames. Honestly, that alone justifies the shift for me.
Sure.
But the part that actually surprised me was what happens when the machine is actually running. Like, the real aha moment for the buyer doesn't just happen during assembly.
No, it doesn't.
It happens when you turn the power on and look at the actual physics of a lighter machine in motion.
Because the operational benefits of shedding all that heavy steel, they compound in ways that directly impact the factory's bottom line.
Here's where it gets really interesting. Let's talk about the inertia problem.
Yeah.
We mentioned the violent back and forth of a loom. The classic analogy people use for energy savings is running a marathon with a heavy backpack. Take the backpack off and use less energy.
Right.
But that doesn't really capture the mechanics here, does it?
No, continuous linear motion is different.
A better way to think about it is, well, holding a heavy bowling ball in your hand and trying to swing your arm back and forth like a pendulum as fast as you possibly can.
Oh man, your wrist and shoulder would snap almost immediately.
Exactly. The sheer energy required just to reverse the direction of that heavy mass at the bottom of the swing is immense.
Yeah.
Now, swap that bowling ball for a hollow plastic wiffle ball. You can flick it back and forth effortlessly.
Right.
The motor driving a textile machine is acting like your wrist. Every time a loom shuttle changes direction, the motor has to overcome the inertia of the machine's own weight.
Ah, I see.
Less structural weight from the aluminum frame means drastically less mechanical strain on the servos and motors.
So they don't have to work nearly as hard to achieve the same speeds. Right. It allows for much faster overall operational speeds and, importantly, a drastic reduction in electricity consumption on every single cycle of the machine.
And when a loom is making millions of passes a month, that drop in electrical draw is literally a massive financial saving.
It adds up incredibly fast.
But it isn't just about weight and inertia, right? The thermodynamics of this setup are equally crucial.
Yes, thermal management is a huge factor in high-speed manufacturing.
Because things get hot.
Very hot. These industrial motors and electronic control boards generate a tremendous amount of heat. And if you mount them to a heavy steel frame, well, steel doesn't dissipate heat very well.
Okay.
The heat builds up, it soaks into the metal, leading to thermal expansion of the parts and eventually the failure of the electronics.
But aluminum is different.
Very different. Aluminum naturally acts as an excellent heat sink. Its thermal conductivity is much higher than steel's. So the aluminum frame actively pulls the heat away from those hardworking motors and electronics, spreading it out along those extruded profiles and basically dissipating it into the air.
Wait, so the physical skeleton of the machine is literally doubling as a passive cooling system.
Exactly. And if we connect this to the bigger picture, when you combine a cooler operating temperature with the precision alignment of these lightweight components, the results are staggering.
Yeah.
The Eleanor Industries article notes that manufacturers who upgrade to these aluminum systems are reporting up to 20 to 30% lower maintenance costs.
Wait, 30%?
Up to 30%, yeah.
That is a massive chunk of the operating budget just handed right back to the factory.
It is. I mean, you have less motor strain because of the reduced weight, you have cooler electronics because of the heat dissipation, and the tight geometric tolerances of the precision aluminum, reducing mechanical wear and tear.
It all equals a massive drop in unexpected downtime.
The machines just run.
Okay, so if the math is this good, faster speeds, lower electricity bills, a huge drop in maintenance, and modular flexibility, why isn't every factory floor already 100% aluminum? Like, what's the catch?
There is a catch.
Right, because the source material outlines some major traps that buyers fall into when they're trying to make this switch.
The catch is that not all aluminum is created equal.
Okay.
And if a factory manager hears about all these benefits and just rushes out to buy the absolute cheapest generic aluminum profiles they can find, they are going to face a catastrophic failure.
So what does this all mean? How does a buyer navigate this without getting completely scammed by inferior parts? Let's walk through those traps, starting with the actual chemistry of the metal.
Yeah, you can't just melt down old soda cans and build a high-speed loom.
Right.
The alloy grades are critical here. Aluminum is naturally soft, so it has to be alloyed mixed with other elements to gain strength.
What does the source recommend?
It specifically calls out the 60R61 and 6063 alloy grades as the absolute standard for this kind of machinery.
Okay, but what do those numbers actually mean in practice?
They indicate the specific blend of elements in the metal. So the 6000 series alloys primarily use magnesium and silicon.
What?
The magnesium dramatically increases the structural strength of the metal, while the silicon lowers the melting temperature and improves how well it flows through that extrusion die we talked about earlier.
Oh, that makes sense.
This specific metallurgical blend provides the exact right balance of high structural integrity and formability.
But if they don't use that blend,
If a buyer cheapens out and uses a lesser grade, the frame just won't have the tensile strength required. It will literally warp under the constant vibration of the textile process.
okay, so you absolutely need the right chemistry,
Yeah.
but then there is the finish. Because bare metal, even 6cc61 aluminum, isn't enough to survive that hostile, lint-filled, chemical-heavy factory environment we were talking about at the start.
Correct. While bare aluminum won't rust exactly like steel, it will still oxidize and pit over time when exposed to harsh industrial dyes and constant humidity.
Right.
To truly survive, it needs a specialized surface treatment. It must be anodized or powder-coated.
And anodizing is fascinating because it's not just like a coat of paint, right?
Not at all. Anodizing is an electrochemical process.
Okay.
You submerge the extruded aluminum in an acid electrolyte bath, and then you pass an electric current right through it. This forces oxygen ions to combine with the aluminum atoms on the surface. You are literally growing a layer of aluminum oxide directly out of the base metal.
And aluminum oxide is incredibly hard.
It is practically as hard as a sapphire.
Wow.
It creates this porous, protective outer shell that is fully integrated with the metal beneath it, so it can't peel or flake off like paint would. It seals the metal completely against the humidity and chemicals.
Okay, so with all this complexity, how is a buyer supposed to navigate this? Because the trap is incredibly tempting.
Oh, very.
Like a supplier offers a quote for generic aluminum profiles that look identical to the 6061 anodized ones, but they cost like half as much.
The trap is devastating, and honestly, it happens all the time. If you buy cheap, inferior alloys, yes, you get premature wear. But more importantly, you lose dimensional accuracy.
Because cheap extrusions aren't precise.
Exactly. When you assemble a machine using T-slots, you are relying entirely on the geometry of the metal to ensure everything is perfectly aligned.
Right, the precision is everything.
If a cheap extrusion is off by even a fraction of a millimeter, if the angle is just slightly skewed, it completely ruins the tight tolerances needed for the machine to operate.
Oh, I see.
When a loom is moving that fast, a single millimeter of misalignment causes the machine to bind up, the fabric tears, the bearings shatter, and you have basically lost all your efficiency gains.
So the cheap option ends up being the most expensive mistake a factory can possibly make.
Without a doubt. And this is exactly why the source is so adamant about the solution. You must work with integrated extrusion manufacturers.
Right.
The article highlights the companies leading this industry in India who handle the entire life cycle of the part under one roof.
So by integrated, they mean the facility does the raw extrusion, they do the machining to cut it to the exact size, and they do the chemical finishing all in the same building.
Yes. Having everything under one single roof is the only way to guarantee those extreme tolerances.
Right.
They use CNC machine and computer numerical control, where computer-guided drills and saws make cuts with microscopic precision.
Wow.
When the same engineering team is responsible for formulating the alloy, designing the extrusion die, running the CNC machines, and managing the anodizing bath, they can control every single variable.
That's amazing. There's no finger pointing between 5 different subcontractors when a part doesn't fit.
Exactly. And it also ensures reliable spare part availability. If you need a replacement structural channel, say 5 years down the road, an integrated manufacturer has the exact digital file, the exact alloy recipe, and the exact die to recreate it perfectly.
It really all comes down to controlling the variables and, looking at the big picture.
Absolutely.
Let's zoom out for a second from the factory floor because the overarching lesson here is so incredibly broadly applicable.
It really is.
We started with this image of heavy, rusting, welded steel machines, these inflexible giants of industry that are totally impossible to change.
Yeah.
And we discovered this brilliant world of modular engineered aluminum T-slots, a structural system that allows massive machines to run faster, shed heat efficiently, and require significantly less maintenance just by rethinking the foundational material.
It is a perfect case study in looking past the initial raw material cost.
Right.
Yes, precision extruded anodized 6061 aluminum might have a higher upfront price tag than cheap, heavy steel.
But the long game.
The long game. When you factor in the energy savings from moving less mass, the 30% reduction in maintenance, and the ability to dynamically upgrade the machine later without a welding torch,
Yeah.
the true life cycle return on investment is drastically superior.
And that framework, that mindset, applies to you no matter what field you are in. Whether you are building a complex software stack, structuring a team of people, or investing in actual physical infrastructure, you have to ask yourself, what kind of foundation are you actually buying?
Are you buying heavy, inflexible steel?
Right. Systems that are permanently welded together and require a massive, painful disruption to change. Or are you investing in modular, adaptable aluminum? Systems designed from day one to grow, slide, and shift as your needs change.
Because in a world that is constantly changing, the flexibility to adapt without tearing everything down is often the single most valuable asset you can engineer into any system.
Absolutely. So we want to leave you with a final thought to mull over. Next time you look at a piece of heavy, permanent infrastructure in your own life, whether it's the rigid organizational chart of your company, a legacy software program everyone is afraid to touch, or even the literal bones of your office building, ask yourself, was this built to last forever, or was it built to change?
It's a great question.
Because in the modern world, permanence might just be another word for obsolescence. Think about where you could introduce a little modularity. The blueprint for your own aluminum T-slot revolution might just be waiting to be discovered.